Okay, so we're going to take a look at filters and what they do to different sounds. Sorry, my levels are too high here. There we go. Is that better? That's better. All right. So we're going to take a look at filters and what they can do to sound. So the first thing I'm going to do, go ahead and open up Audacity. For this one, it's Audacity the whole way through. We're kind of just doing sound processing this time. So like I said before, WaveSurfer is really good for looking at speech and teasing apart the differences, the nuances of speech and looking at that. Audacity is really more of an audio editing program, which we're not doing a whole lot of audio editing in this class, but uh, today is a little bit of audio editing. So we're going to open up Audacity. And what I want you to do is go up here to Generate and go to Noise. You've got a few options. You've got white, pink, and brown. Basically, the difference is white noise is going to be full spectrum. It means that every frequency has equal likelihood of being represented in this type of noise. Pink noise is a little bit more weighted towards the low end, and brown noise is heavily weighted towards the low end. So they will sound like kind of like that. It just gets progressively lower. So what I want you to do is go ahead and generate a white noise. Your amplitude should be 1. Yeah, your amplitude should be 1. I'm going to do 1.5 seconds. You can do 1.5, you do 1. It doesn't matter. The way to set that in here is just, so if you wanted to go 1 second, you'd go 1, 0, and now it's set to 1 second. So I guess I'll do 1 second. So here's 1 second of white noise. And let me open up a audio capture so you can hear what this sounds like. All right. Hopefully it's not too loud. So here's white noise. That was too loud. Sorry about your ears. Let me turn that down. Okay, here's white noise at a much more manageable level. I should cut this out, but I'm not going to. I feel like it's funny. Okay, there's some white noise. And now we're going to make some brown noise. So one thing that you have to do, if you're generating tones in Audacity, you have to click off of the first tone that you made. If you don't, it's going to overwrite that tone with something else. So if we put brown noise on, we won't have 2 tones. We'll have brown noise over top of the white noise. The white noise would be gone. You have to click in this gray space of nothingness out here. So now go up, generate noise right there, and brown. And we'll click OK. And they look a lot different, and that's because brown noise, in addition to giving you kind of a lower weighting spectrum to the noise, so we've got definitely like lower frequencies. It changes incrementally. So Brownian walk is kind of like you start at a random place, and if it's a random motion, it could go from this random space, which let's say it's 10 to 10 hertz. The random movement of white noise could go up to 2000 hertz immediately, and then back to like 5 hertz, and then 300 hertz, something like that. It's just moving around all wildly. Brownian motion is a random direction, but it doesn't go very far. So if it starts at 100 hertz, then you don't know which direction it's going to go, but it might go to 300 hertz or 50 hertz or something like that. So it's going to stay in this little range, and it's going to randomly go in any direction. You can almost think of it as the path of an ant, because that's actually Brownian motion as well. So sometimes they walk faster, sometimes they walk slower. So if you're looking at where an ant is at every second, their direction is kind of random and their speed is a little bit random. So how far? But they're not going to like teleport to the other side of a field. It's going to be kind of localized. So that's Brownian noise. Anyway, that's like way more than you need to know. So I'm going to solo this brown noise track. So that's the only thing that you're going to hear. And I'm going to play it. It's soothing, isn't it? I mean, if you have trouble sleeping, I would say go into Audacity and generate like 3 hours of brown noise and just sit and listen to that. Okay, so now I'm going to unsolo this. We're going to put a filter on our noise. Actually, before we do that, let's get a look at the spectrum. So let's select it all. So what I'm going to do is I'm going to hit Control A, click in the white noise, and then I'm going to hit Control A. Ah, shoot. That's what I was worried about. It actually selected both of them. So forget I said that. You're going to have to just use your mouse to select all of white noise. So we're selecting it all. We're going to come up here to Analyze, Plot Spectrum, and here's the spectrum of our noise. It should be noise. This shouldn't look, periodic in any way, and it really doesn't. So we've got a fundamental, if you can really call it that, at 59 hertz, and then another peak at 143. If this was harmonic, we wouldn't expect the next peak to be at 143. We'd expect it to be at 2 times 59, which is 118. So this is far beyond that. And then this is way too close, 222. And then we've got another peak at 250, 313. So there's like really no rhyme or reason where these peaks are here, which is exactly what you'd expect from a noisy signal. Okay. Now, what happens if we select just a little bit? Do we get the same thing? No, we get 74, 156, 306, 462. So this is saying that from, if you select the whole thing where the average peaks are, or just in this little time frame that I've selected, we're seeing different peaks. Again, it's noise. So you'd expect the average peaks to change from time to time. Okay, now brown noise is noise, as you would expect from its name, but it's not as random as white noise. So we should see a little bit of a different look here. Whoops. How crazy is that? Perfect brown noise. So there's not really a peak. There's not a measurable peak that we can see, even if I bring down the size of the window. Not a measurable peak. It's just falling. All of the frequencies are there. You can see that there is more power at lower frequencies than there is at high frequencies. With the white noise, there were peaks, but it was pretty much flat power spectrum across the whole thing. Let's close this and let's take just a little bit of brown noise. On spectrum. Now we're starting to get some peaks that we can actually kind of identify, but overall, we've still got this decreasing power spectrum. So it's kind of like we took white noise, which if you took the average of white noise like this and we went, wah, we just kind of made it drop off. Almost like we put a filter on the white noise. Interesting. Okay, so we're going to close this. I'm going to highlight all of our white noise again. And if you're following along, I think you're going to have some fun with this. Ah, shoot. Okay. Highlighted. Hooray. So now we're going to go to Effect and Equalization. So this is going to bring up kind of an equalizer. If you're into audio editing, you can do this with like an EQ board where you have like different sliders for these different bands, and you can like push them up or pull them down, and that just says you're allowing sound to come through if it's up or not if it's all the way down. We can do that here digitally as well. What I want to do is I want to make our white noise look like our brown noise by making a filter. So the EQ right here is a filter. And this is going to look like all the filters that you've learned about throughout this module, right? This looks like we've got a filter that's coming up and it's going across and it's coming down. It's going to let through, well, actually, let's put it this way. It's going to impede all frequencies from 20 hertz to about 50 hertz, the way it is right now. I'm going to move this over so we can just say 50 hertz. Okay, so it's impeding everything from 20 to 50 hertz. That's not going to be in the signal at all. Likewise, anything between 7,000 and up, 7,000 and greater, is being impeded as well. 7,000, yeah. I think it was 70,000. Everything from 7,000 up is being impeded as well. Actually, that's 8,000. Sorry about that. Because this is 7,000. Everything between 7,000 and 60 hertz is being put through as it was. So what you'd see here is like really high frequencies are gone, really low frequencies are gone. And really we're only seeing things between somewhere about 50 hertz to 8,000 hertz, but the peak is at 60 and 7,000. So it's really 60 to 7,000 hertz. Now that's our blue line. You can also see this little green line here. What is that green line? Well, that's telling you what's actually coming through. So we can set the filter with the blue line. And that's what we're setting. But then the green line is going to give us, like, in reality, what can the filter actually do? So we can set it up, and the green line is showing us, like, you can set this up this way, but you're still going to expect some frequencies at these very low frequencies over here between the green line and the blue. So this is what's actually going to be there. This is what, in theory, is going to be there. And that's okay. You see that it's rolling off. It's getting a lot quieter. So the power of those frequencies is going to be very low. But they're not going to be as non-existent as we would like. Now over here in the high frequency, our green line follows our filter pretty well. And that's because it's higher frequency. We're able to follow our curves more closely, just due to the nature of the sound up there. The sound frequencies are traveling a lot faster, so it's easier for us to put on a curve. What I'm saying is, if you have a filter whose bandwidth is 20 hertz, well, over here at 50 hertz, that's quite large. It's 30 to 70. So you have a bandwidth, or sorry, that's totally wrong. I'm adding 20 to each side. Your bandwidth is going to be from 40 to 60 if you're centering on 50 hertz. But if you're over here at 8,000 hertz, well, now you're at 7,990 to 8,010. And that's much smaller relatively to the frequency that you're centered on, right? So it seems like it works a lot better at the high frequencies. That's just because we don't have as good of frequency resolution up there. Okay, so this is a filter. This is not the filter that I want to use for our white noise. In fact, for our white noise, I'm going to make it look just like the brown noise filter. So let's cut it off. Let's put a cutoff at 10,000 hertz. And we're just going to like roll this off incrementally. Linearly incrementally, I should say. That's about right. So here's our filter. Our filter is cutting through it like a sword. I'm going to click OK. Aha. Now let's take a listen to that sound signal. We're going to solo it. That means solo is just this track that's playing, like a guitar solo. You can also mute tracks, and that means you're just muting one. When you only have two, they're essentially the same thing. I could mute, and you can actually see that here. This has been muted when I click on solo. So when I solo this one, this gets muted. If I mute this one, this becomes the solo track. If you have more tracks, it is a little different, because then if you have three tracks, mute is taking one out and you hear the other two. Solo only lets you hear that one, takes out the other two. Okay, so let's see what this sounds like. Sounds like nothing. Interesting. Remember what it sounded like before. In fact, let me undo and let me turn my sound down a lot. White noise. Edit, redo equalization, bump the sound way up. That sounds a lot more like brown noise to me. Here is the brown noise. They sound very similar, right? We've used the filter to change the white noise into brown noise. So let's take a look at the spectrum. No. There we go. Analyze, plot spectrum. Beautiful. Looks exactly like our brown noise. Very cool. Okay, let me show you something else. We'll undo the equalization here, but I do still want to highlight all of our white noise. Go back to effect, go to equalization. Now what we're going to do is I want to highlight a couple frequencies. I like 200 hertz for some reason. I don't know why. So let's go 200 hertz. I don't want that to be super wide. 100 hertz is about it. It feels good. And we'll take it down 100 hertz on this side. So we had a 200 hertz bandwidth centered on 200 hertz. I like the symmetry of that. It's nice. And then let's also, what the hell? We'll bring up 2000 hertz as well. Let's put that roughly on 1500. You got to click on these to drag them up, but I think, there we go. We'll put our other dot right here at 2000, and we will bring another dot to 2500. So this one is a little wider. It doesn't look wider, but it's 1500 to 2500. It's 1000 hertz centered on 2000 hertz. The other one is 200 hertz centered on 200 hertz. Why does it look wider? Because this is a logarithmic scale, and our perception of sound is also on a logarithmic scale. So we have a lot greater frequency discrimination down here than we do up here. Okay, so let's click OK. We're going to filter our white noise to these frequencies. And now you can see like actual waves in there. So what this should have done is I should have dampened out everything that's not 200 hertz and 2000 hertz. And we've got some slop on either side of those. So first, what we want to do is let's listen to it. Let me boost my sound. This is a totally creepy sound. I like it. Let me use that as a ringtone. Yeah, it's cool. Okay. So now let's take a look at the sound, the spectrum. Oh, wonderful. It's exactly what we wanted to see from our filter, perfectly. So we're centered on 203, it's, within tolerance, and 1989 within tolerance. This is amazing. Okay, so let's zoom in just a little bit. Take a look at what the waves actually look like. Isn't that cool? So it looks like what we have is the fast moving waves, that's probably 2000 hertz, and the slow moving waves uh, is probably 200 hertz. So we've got like that's 200, I'm guessing, and then the very fast one is 2000. We can check this ourselves, right? Although it's getting a little hard to see the large wave here. Let's say it crosses the zero about here, goes up, across the zero again, down, and crosses the zero about here. And it looks like our start is 0.226 seconds. The length is 0.05. Let's look at start and end. 0.226 to 0.232 seconds. That's still kind of giving us a rounding, but that's okay. 226 to 232. Let's do some quick mental math. 4, 5, 6. So it's 0.006 seconds. Use our good old formula here. $166. Yeah, it's close. It's close to 200. So what I did was I put 1 over the period of this wave, which, of course, is kind of not totally exact because I'm measuring it with Audacity here, which rounds, which isn't great. We could estimate it a little bit more. We could say 0.225, 0.226. That looks like 0.22625. But actually we're going to need to do, and then this looks like 0.23175 possibly. So let's 0.23175 minus 0.22625 equals 0.0055. So 1 divided by 0.0055, 181. So it's a little bit closer to 200. And it's within tolerance, right? We set our filter to go from 100 hertz to 300 hertz, centered on 200 hertz. So we should be pulling a frequency that's around 200 hertz, but within those tolerances. And we are. So that's very cool. If we zoom in, and we grab this frequency right here, well, that's too short for us to actually even see with Audacity, so we're just going to have to assume that it's probably around 2000 hertz. But anyway, there you go. That is, let's zoom out and take a look at this again. So that's how a filter works, even with white noise. See what it looks like in here. Oh, there we go. There's a lot of, must have been a lot of 2000 hertz information in this area that was able to come through because we've got quite a bit of amplitude right here. And then you can see like in here, right here, there wasn't much 2000 hertz energy. So we can let it come through, but it wasn't, there's not anything there. You can't amplify something that doesn't exist. So here there was a lot of 2000 hertz energy. Here there wasn't. We're just allowing it to come through. Cool. All right, so that's filters. Here's what I want you to do. I want you to, for your assignment, use what I just showed you and make your own filter. Remember how you do that is you go to Effect, Equalization, and then, okay, Equalization, and then you have a filter. What I want you to do is take a screenshot of your filter. You can take a screenshot with print screen, the key called print screen. Sometimes it's PRT-SC or SRC. Sometimes it actually says print screen. Hit that screen, open up Paint or PowerPoint or whatever, Word, and then you can paste what you've gotten from print screen. You paste it with Control V. So just like you're pasting something that you've copied. Basically what print screen does is it takes a copy of everything on your screen, puts it on your clipboard, and then you can paste it anywhere. So go ahead and take a picture of your filter, paste it somewhere. I want you to put your filter on your own white noise. So generate some white noise, open up the equalization, make whatever filter you want. You can have 1 peak, 2 peaks, 3 peaks. Go crazy with the number of peaks. Go crazy with how wide or skinny they are, or even their shape. They don't have to be pyramids. They can be kind of like flat pyramids. Or you can make something that's like, you could even do this, where it's not all or nothing. The middle could be something you let through some information in the middle, but not all of it. So you kind of make like cat's ears that you're drawing. So do that. Apply your filter to the entire amount of white noise. And then I also want to see a screenshot of your spectrum. So what you do there is we've got this highlighted. You go into Analyze, Plot Spectrum, and that's what I want to see. So I want to see your filter. I want to see your spectrum. That's what you're going to upload for your assignment. Okay, great. I will see you next time, but in a couple days at the beginning of the next. I'll see you later.